SwayamPrabha. Digital India. Educated India.
Okay, welcome back. We're going to start a new topic. It's on chemical reaction, which is a very integral part of thermodynamics in industrial scale, particularly where the thermal energy is being generated using some kind of a reaction or fuel burning leading to generation of energy. So this is what the overview of this particular topic. I will start with the definition of fuel and combustion. Now, our fuel is basically any material that can be burned to release the thermal energy. The most common fuel consists of primarily hydrogen and carbon in terms of hydrocarbon, which is a commonly known fuel, and this general formula is CnHm. Okay. Now, a typical distillation column or the separation of the crude oil, which separate based on the density, for example, is illustrated in this form, where different types of fuel is separated, such as gasoline, kerosene, diesel oil, diesel fuel, fuel oil. These are all hydrocarbon fuels which exist in different phases at normal conditions. Some in gas phase, some in solid phase, okay, depending on the densities. The most common hydrofuel is basically octane, for example, okay, and natural gas, for example, is another one which consists of mainly methane. Okay, now in addition, one can have other kind of hydrocarbon fuel which are consist of methyl alcohol or methanol. Okay, which is commonly also used nowadays as in different existing fuel to create some kind of blended fuel. This is mainly because to reduce the content of CO2 out in atmosphere, or in another word, to make it more environmentally friendly. And thus these new alternative fuels are becoming more important, increasingly important in current usage in industry as well as in automobile industry. Okay, and thus we need a friendlier fuels for the environment, and importance of natural gas, alcohol, LPGs, hydrogen is becoming increasingly important. Now one can look at this table which provides energy contents of different kind of fuel, considering gasoline as a basis for the energy content, and one can clearly see is that your LPGs, ethanol, CNGs, these have a high energy content, and thus it's also useful that you want to burn the same amount of mass but obtain much higher amount of energy based on this particular table illustrates that, and thus it's becoming quite relevant to make use of such kind of fuels in daily usage. Okay, so one of the primary thing which primary physics behind this energy generation is combustion, and thus we need to little bit spend some time on it. Combustion is nothing but a chemical reaction, okay, during which fuel, which we already discussed, different kind of fuel, is oxidized and a large quantity of energy is being generated. So this is basically combustion, and thus we need an oxidizer which is mainly air, but in many cases oxidizer would be a pure O2, such as used for in cutting and welding. Okay, air will contain not only oxygen but as well as nitrogen. Okay, so if you consider 1 kilomole of oxygen, the corresponding number of moles of nitrogen is 3.76, and thus the total amount of air would be 4.76 kilomole. Okay, nitrogen acts like an inert. Okay, we will be assuming that it basically it behaves more like an inert gas, and thus it will enter as a reactant as well as a reactant or in a reactant species, but as well as it will exit in the product phase as nitrogen itself. So though it acts like a inert gas, but it will affect the outcome of the combustion, okay, because it enters typically at low temperature but exit at considerably high temperature, okay, and thus it absorbs a large portion of the chemical energy which is being released during the combustion. Okay, thus it will also affect the outcome of the combustion. Okay, so let me go through a bit of the mass balance, and so one can clearly see based on a little bit of exercise that the moles are not going to be balanced during the chemical reaction. It's only the mass of the elements which are going to be balanced. Take an example of generation or the formation of a carbon dioxide from a simple carbon element and oxygen leading to CO2. Thus, you have 1 mole of carbon plus 1 mole of oxygen leading to 1 mole of CO2. Clearly, one can see that moles are not balanced. On the other hand, the mass of individual elements are balanced, which one can see here. Okay. Now, mass is connected to the number of mole and the molar mass from this expression. Okay. The chemical equations are balanced on the basis of the conservation of mass principle or the mass balance, okay, which we state as follows: the total mass of each element is conserved during a chemical reaction. For example, in the case of water formation from hydrogen and oxygen, 2 kg of water and plus 16 kg of oxygen leads to 2 kg of hydrogen and 16 kg of oxygen, which is part of the water. Okay, though the number of moles are different because here is 1 mole and this is half mole, okay, leading to 1 mole of water. So in this case, we need to balance hydrogen, which should be balanced, and as well as oxygen. So clearly the reactant, which is this, contains 2 kg of hydrogen and oxygen 16 kg, and as well as this would be the same for the product case, okay, as you can clearly see from the water. So that is how we are going to make use of it in the analysis as well. Later on, we will clearly use this mass balance for our analysis. Okay. Now, the fuel automatically does not burn by itself, and well, this is good, otherwise it will be burning all the time. So it requires a certain kind of temperature at which it will start igniting itself. Okay, and this is what we call it ignition temperature. Okay, so ignition temperature is the temperature which is the minimum temperature at which the combustion occurs for the fuel. So, for example, for gasoline it is 260 degrees Celsius, carbon 400 degrees Celsius, hydrogen 580 degrees Celsius, carbon monoxide 610 degrees Celsius, and 630 degrees Celsius for methane. Okay. In addition to this, you need a sufficient amount of oxidizer, or for example air, for burning a fuel. So a proportion of the fuel and air must be in a proper range for combustion to begin. For example, natural gas does not burn in air in concentration less than 5% or greater than about 15%. So this is something is quite relevant, that there is a certain range of oxidizer or air which is required in order to burn the fuel, okay, or in order to combustion to occur. So which means there is a certain air fuel ratio which is necessary. So let us first define what is air fuel ratio. So the air fuel ratio is nothing but the ratio of the mass of air to the mass of fuel. So it's defined on the basis of mass. So AF is, with an acronym for air fuel ratio, is nothing but MA air divided by M fuel. Okay, for example, this is the fuel as a reactant and air. Okay, this is a reactant leading to combustion, or in combustion chamber leading to product. So in this case, the air fuel ratio is nothing but 17, is like 17 kg of air divided by 1 kg of fuel. Okay, the reciprocal of air fuel ratio is fuel air ratio. Okay, so this is sometimes used, but most commonly used is AF ratio. So the air fuel ratio represents the amount of air used per unit mass of fuel during a combustion process. So this is sometimes a terminology which we use in order to solve the problem. So let's take an example to find out the number of moles for each gas and as well as the air fuel ratio for the combustion chamber. So this is an example of 1 kilomole of octane which is burned with air. Okay, so this contains 20 kilomole of O2. Assuming that the product contains only CO2, H2, O2, N2, determine the mole number of each gas in the product and the AF ratio for this combustion process. So the first thing what we are going to do is to write the chemical reaction or the equation here. So octane is C8, it's already assumed to be 1 mole, so this becomes 1. Okay, so basically it's nothing but 1 into C8H8 plus 20 kilomole of air. So air contains O2 plus 3.76 of nitrogen. So I'm going to write here 20, which is being multiplied here. This leads to product species, and we don't know the moles of those these products, so hence we are going to use whatever is written here, XYZ. So X CO2 plus Y H2 plus Z O2 plus WN2. Okay. Now we know that the mole are not going to be balanced. So the first thing is to do a mass balance of each species. Okay, so let me start the exercise here. So the mass balance, or you can also make use of total number of atoms. Okay, it's the same thing because the molar mass will get cancelled among the right hand side and left hand side of the equation. So one can do simple total number of atoms instead of writing the complete mass balance. So for example, so I can write 8, this multiplied because there are 8 atoms, this multiplied by its atomic mass is equal to x multiplied by atomic mass. The atomic mass will get cancelled, so simply 8 is nothing but x. Okay. Similarly, I can write for H 18 hydrogen atoms should be equal to, hydrogen is here only in water, so this becomes your 2 times y. So this means y is nothing but 9, okay, x is nothing but 8, and then you have this O, oxygen. Oxygen on the left hand side is 20 times 2, these many atoms. This should be 2 times x plus y plus z into 2, okay, and if you plug these values you can get z is 7.5, okay. Similarly, N2 is 20 times 2 times 3.7 here. So either you can write N2. If you're writing N2, then I should erase this because this is only the balance of N2, okay, not N, but it will be more or less same, or it will yield the same results, and this should be equal to W. Okay, I can also write this for N is equivalent 20 into 2, 3.76, 2 into W. So this is equivalent to this expression, and this gives W as 75.2. Okay. Now I can write down the air fuel ratio, which is nothing but m air by m fuel. Okay, the mass is nothing but your n number of moles multiplied by molar mass. So this can be written as Nm for air, and for the case of fuel, now fuel consists of carbon and hydrogen. Okay, so I can write N m of carbon plus Nm of hydrogen, which can further be written as the number of moles for air is 20 into 4.76, that will be total number of kilomoles, okay, multiplied by 29 kg per kg mole, okay, kg mole here, divided by the number of kilomoles for carbon is going to be 8 only, okay. So because the number of carbons are 8, so we are taking 1 kilomole as a basis for the fuel, so that becomes total number of moles for carbon. It is going to be 8 kilomole, corresponds to 12 kg per kilomole, okay. And similarly for hydrogen, is going to be your 18. So 18 is a hydrogen atom, but for H2, okay, is going to be 9, correspondingly 9 kilomole. You can also write the same expression for hydrogen atom instead of H2. So 9 kilomole multiplied by 2 kg per kilomole, okay. So this gives us 24.2 kg of air per kg of fuel, okay. That's your air fuel ratio. So this means that 24.2 kg of air is used to burn each kg of fuel during this combustion okay, process. Okay. So that way what we have done, we have determined the moles, and this was determined by calculating the balance by performing the mass balance for each individual elements, and leading to this number of moles for the product streams, product species. In addition, we also calculate the air fuel ratio. So this is a simple exercise to illustrate how to go about solving such problems. Okay, so that will be the end of this particular lecture. In the next lecture, I am going to describe a bit of combustion analysis, and as well as some for the reacting systems for both steady state and fixed mass systems. Okay, so see you in the next lecture.